Hello and welcome back to Compiler Programming. Today's video is going to be slightly different in that I'm not actually going to be coding anything. Instead, I wanted to take a thorough look at the way we are structuring our encoding code and instruction code and see if the way that it's going is actually how we want to continue with it. Because as we discovered in previous video, there is this issue, for example, that we have specific encoding that is only happening when one of the operands is specifically a byte. Then we don't really have right now a way to say that, for example, we are going from a byte to 16 bits or 32 bits or 64 bits in encoding. So like these enum is basically not really capturing the whole variety of x86 64 instruction set, and we are not even getting to floats and vectors and all kinds of stuff that are more advanced. So I think now that there is a bit of code inside the language and there is a bit of understanding of how we are actually using it and what we want to get out of this, it might be a good time to at least reevaluate if the approach that is currently taken is a good one, or maybe if we can do something better. Another thing to consider is right now all of this code focuses exclusively on x86, but long term I would really like if we could support ARM processors, and if I just open the Firefox to get to Compiler Explorer, you will see that ARM instructions look really, really different. Like it's reduced instruction set versus I think complex instruction set, CISC, I think that's how it's called. Yeah, so one of them is complex instruction set, the other one I believe is reduced instruction set. And like x86 is complex instruction set, because as you see, there are all of these different ways to load stuff from memory, load stuff from registers, the operations on memory, the operations on registers, and internally it still converts them to the same stuff. So like, for example, the instructions you see here are not actually things that the processor executes. A lot of them are mapping to simpler like RISC style instructions anyway inside of the CPU, and all of this is more or less treated as a programming language, and inside of every CPU or every x86 CPU you have another compiler that gets this stuff and compiles it down to actual I think it's called microcode that CPU executes, but I'm not very well versed in the terminology, so don't quote me on that. Anyway, what I wanted to show here is that if we go to the full version of this, we can actually change even for Windows, there are ARM processors. And if you look at how that looks like, it's quite a bit different from what we have. Like, for example, there seems to be that there are immediate operand instructions, like add supports immediate, and but besides that, a lot of the stuff should operate on registers. And there are a lot more registers, I believe, in our CPUs. So that's also something kind of different. So our code ideally should not assume how many registers are there in CPU. Again, while I don't necessarily care about all the other architectures, ARM and x64 is what I'm interested in. So let's recap again how we are doing it right now. We have this format, which is we call instruction, that consists of a mnemonic, which is a name that we can use for debugging, Then there is a list of encodings for this instruction, and this is just a counter for the array because C. And then we have this loop where we match the operand type versus the encoding type. And while they are similar, they are not always a direct match. So like when you have register, it's fine, but register can be coded in different ways. In instruction, for example, there could be explicit registers, there could be opcode plus register, there can be something that accepts either register or memory. So like it's not a one-to-one mapping for at least x86 instruction set. One final thing is that even for memory, we kind of have several different types of memory, I'd say. So we have this RIP relative addressing, where we are just doing the offset from the current instruction pointer, so current point where we're executing the program. Then we have the indirect memory access, where we say that, okay, the address is stored inside of the register, and then we take that database and we can either just take its address verbatim, or we can add some offset to that address. And we didn't really go into this scaled index byte mode, but it's even more different, where you essentially have two registers. One of them acts as a base and another one acts as an index. So this is traditionally used for loops where you would store like index inside of a register, and then you use SIP instructions to do this iteration over elements, which allows you to kind of efficiently go through that array without moving the original pointer. So yeah, this is the stuff that we're doing right now. And while I'm pretty happy with the main loop in general that does the actual encoding, I'm not entirely certain that this is a good idea, and the fact that we automatically search for the right encoding. Because if we also look into, like, not sure if it is this file, or I guess we want to have function. So if we look into here and we look into, for example, move, right? First of all, when we on a high level say that to move a value, it might be move instruction, which is very straightforward. It might be different instructions. It might be several instructions. So there is not even one-to-one mapping on this level. And even more awkward, I'd say, is the fact that right now this code sort of has knowledge about this kind of stuff. So like we have to know that, for example, there is no way to go from a immediate 64 to memory in our code here, but this information is also encoded in here. So this is a bit nasty as far as isolation goes. So there these two things quite tied together. And then we also have the situation where we have these patches floating around, right? So in where we're doing encoding over here, we are kind of like saving a patch to where was it? Yeah, so for the stack displacements, instead of encoding them directly, we are just saving them. And all of that seems a bit nasty. I mean, maybe this is just, so there is accidental complaint, accidental and incidental, I believe it's the good terminology. So let's make sure that I'm using words correctly. Incidental. Okay, this is not even look. Meaning so accidental, I can exactly by chance. Okay. Not sure I'm using it correctly. Anyway, there is stuff that is basically inherently complex that you just can't get away from it. Like, I mean, as we see, the instruction set of x86 CPU is complex. I mean, it's even called complex instruction set, right? So we have to deal with that somehow. But on the other hand, the question is our program just enough complex to handle that, or is more complex than it needs to be? Or maybe it's also nice if we can kind of hold all of this complexity in one place instead of spreading it all across the program as it is right now. So all of those are questions that would be interesting to try to answer and see if we're just doing the best we can. So what I want to do is now jump into some painting app and try to visualize for myself what are the different things that I just listed. So let's recap. So the first thing is, let's start with where are our things can be stored. So we have registers, right? We have registers, and registers are kind of interesting by themselves, at least on x86. But I think I will, to simplify things for now, and this will probably carry us quite far, is to ignore the fact that there are non-general registers. We will have to deal with them eventually, but maybe it's okay if we forget about them for now. So let's say that registers are, I'm only targeting, so first of all, let's do this. So I'm interested in x86 64 and ARM. That's 64. And I know my handwriting is quite terrible, but I will verbalize everything I write, so bear with me. Okay, so I'm only interested in 64-bit architectures at the moment. And for simplifications of the program, I just assume that all registers are 64-bit. And this is the maximum that we can store in them. Again, both architectures actually have wider registers. So ARM, it's a Neon extension, I believe. And on x86, it's SIMD stuff, which is XMM, YMM, ZMM registers that are 128 bits, 256, and 512 bits. And you can do a lot of interesting things with them, but it's not required for any program to function. So anything that you can do with those registers, you can also express using other stuff, right? So for that reason, I'm just going to ignore all of this and say, okay, we have registers. So since we have started to talk about 64 bits, I also want to maybe switch color and say that we have values. And values are important for us in terms of their size. Value, let's call it value sizes. So what value sizes we have? We have, I will put it in bytes. So 1 byte, 2 bytes, and then we have 4 bytes, and we have 8. And these are special till here because they fit into here, right? So these are special. And then we basically have more. So it doesn't really matter what the size is, at least for now, because we are ignoring SIMD registers. So these are essentially different things that we can have. and something we need to at least be able to represent. Now, the more stuff is also interested by itself when we need to figure out how do we represent, for example, arrays, because it's still not really solved in the code. And I did a hack in a couple of tests to actually make that happen, but we need a more general solution to how we deal with that fact, right? So yeah, we need to think about that. Okay, getting back to over here. So we have registers, and maybe I want to erase this somehow. So tools, okay, so it's E for eraser. Okay, let me remove this. Okay, so registers, and I say that is less or equal to 8 bytes. This is what registers are for us. Okay, we have registers. We have memory. These are basically the stuff where it can be. Actually, let me first put something else and then we get back to memory. So we also have immediates. And that just says that we want to specify values directly. The issue is that immediates are also less than 8 bytes, and 8 bytes is special. 8 bytes is special. Because you can only use it essentially with move commands. Of all others, you want to go through a register. So in a sense, if we want to build the most general system, would be good if we could avoid 8 bytes, or maybe not. I don't know. That's just something to think about. Okay, so registers, immediates, and memory. And memory is the most complex of them, of course, because at least in x86 64, there is a lot of ways how to refer to memory. And let's just do kind of maybe subdivision on that and see what it looks like. So in terms of memory, what do we have? We have absolute. And when I say absolute memory, let me erase it and write it better. Absolute. And absolute memory is essentially immediate. So this is this stuff. It doesn't happen often, but it is possible in certain instruction to just say, I want this address, and it could work. Then we have, but like, basically I will avoid this version probably. Next thing that we have in memory is relative. And relative to instruction pointer. So this is, I think, a separate class of things. This is used for jumps. We have function calls that use this, and there is this rep relative addressing, right? This is the stuff that deals with relative IPs, and I would imagine that even on ARM, these two are definitely the same. I'm not sure if ARM has rep relative addressing. That's something I need to research. But even just because these two are essential, we have to support some form of relative addressing. right? So this has to be a thing in whatever system we come up with as we solve this modeling problem. Okay, what else? We also have indirect memory, and let's just say call it indirect. And this is looks like this. So we say array x plus 8, for example. So we take a value that is inside the register and we put some constant next to it. So if you think about it, absolute form is redundant to indirect one. So even if it exists in certain instruction, and I'm actually now that I'm thinking, I'm not sure it does, you could always put it in a register and then just say the offset here is 0, which is perfectly valid, and it will be fine. So I will completely ignore this and just say no. This thing does not exist for us. It will, maybe we will figure out how to optimize things to make that happen, but I will just not do that. And say, no, this does not exist for me. And this is going to be just indirect. Now, when I was talking about relative is also immediate, because the instruction is jump, whatever, -5, right? We want to jump -50 bytes up relative to current instruction pointer. In this case, so from the encoding perspective, -50 is immediate operand, but this immediate operand has very different semantic from like just saying I want to put number -50. So it's very different to saying move array x -50, right? Those are very different things. This is relative and talks about instructions, and this is kind of absolute value and talks about what to put in a register. So it's maybe it will be important for us to distinguish those, because right now they're not distinguished in the code that we have. Okay, we have again this relative IP stuff, and we have indirect things. If we look at certain instructions for x86, then there are instructions that sort of can do either of those things. So they can be memory or they can take a register. So they are RM. Let me check. Okay, yeah. Just checking that you can actually see this part of the screen. Let me check that. Guess it should be fine. Yes. Okay. So yeah, there are instructions that take either register or memory. So this is another complication that we have to think. Now, finally, there is a special case of indirect memory access, which is stack. And stack is exactly the same as this, except we have RSP and then whatever, plus or minus 16. So they are absolutely the same. When we are encoding them, there is a extra problem that we have to use actually SIB encoding for this, but this is, I think this is very incidental to the x86, and it doesn't really matter for us. This is something that we could easily isolate, because apart from the actual code, so if you look at this stuff, apart from actual code that does this, nobody really cares that this is happening. So there is even though in here somewhere, let me find where it actually is happening. Yes. So yeah, we have this thing about stack being special, but no other code knows this. Like there is no special casing anywhere else in our code that has to do with, this RSP register is doing something. So this is a very good like isolation layer. So I'm not too worried about the aspect that SIP has to be used to deal with this stuff. However, I think that stack is special also because we have to calculate that stack space, right? So we have that whole thing about, if you go into here, we have this whole thing about reserving stack, and then there is a bunch of stuff in function begin and function end that has to do with this stack reservation. And we have, because we are also doing single pass encoding, there is this patching setup, and it's kind of not really great, a great thing to deal with. So yeah, that's another thing to think about. So stack is special from the semantic standpoint. It's not as special from the perspective of assembly itself, right? There are special instructions that deal with stack. So more precisely push and pop, which usually exists in majority of assemblies. But in modern code, usually these two are only used in prologue and epilogue of the function. So they are not, like this is not what you would put in the middle of the function, because they screw up all of these offsets for the variables that you have inside the function, and it's not really something that you use unless you're doing assembly yourself, like just writing out instructions manually. None of the compilers, I believe, actually uses push and pop outside of prologue and epilogue of the function. So I think that we can basically ignore it and just put them in again for prologue and epilogue when we wrap function into the value that we want. Okay, it's a bit messy, but this is the kind of a mind map that I have of all the different things that we need. So how do I want to handle it? Well, first thing is, now that we've seen kind of benefits and drawbacks of doing a single pass compilation where we are just writing out things directly, if we eventually want to support several architectures and we want to maybe simplify our life a bit in terms of all of these patches and weird things, it might be a good idea to figure out where the boundaries need to lie. Okay, so let's recap. I think that from the standpoint of application, we have stack as being special. We have other memory that is more or less the same from the standpoint of the program. And registers are, in a sense, irrelevant, right? Unless you're writing assembly directly, the mental model that people have of variables is a mental model of a stack usually, because this is what people are taught and this is how we expect the program to behave, right? If I say int x is 5, right? I can always, for example, in C, do int star p is ampersand x, and I always expect that to work. So I'm saying I want to take an address of this variable that I just defined. But if we introduce registers here, then you sort of can't do that, right? Because you can't take address in the registry. So it also means that if we were to continue doing a single pass compilation and we started to assign registers to variables, we would run into interesting issues with the fact that, okay, we're like, oh, I saw this variable declaration and it's 5, so I'm just gonna put 5 inside a register and then I'm gonna do some operations on it. But then I'm like, oh, but I need to take an address of X and I can't take address of register, so I have to now shove it into stack. And this just doesn't work very well. So again, from the mental model of developers, variables are stack. Or they are, I mean, even if they're memory, they're usually addresses of some memory location encoded in a stack. Because even if I say int x star, int star x is, I don't know, malloc of 4, right? So if I do that, I still, like, I'm storing the address of X on the stack in this case, right? So it's still the same mental model. And whether it is a good thing or a bad thing, it's something to consider. Also, interestingly, if you're not coming from C or C++, then your mental model is slightly different, right? You don't have this operation usually. So if you're talking about something like JavaScript or I believe even C# or whatever, all objects are pointers. And if all objects are pointers, then this operation doesn't exist, but instead you're always dealing with addresses everywhere and you suddenly don't have, like, your stack becomes even less special. And even though something like C#, for example, would, as optimization pass, it would say, oh, actually, like, these objects never leave this function, so I can actually allocate the things on a stack. It still treats everything as a pointer. And maybe that's an interesting semantic to think about as well. Maybe that's how we want to do things. When you define, for example, int x equals 5, it is never actually, like, you cannot define it this way, for example, in our language, and you always get this stuff. So that's sort of interesting, because then the semantics become way simpler, and it may be way simpler to reason about how things are. It also means that maybe we disallow this operator as well, right? You cannot take a address of any variable, or maybe you can, because you'll just get, you'll get ***. And it's just kind of a side note about all of this, that the choice that we have on the encoding of the stuff in a program, it is affected by the semantics of the language itself, because different language semantics end up having different results. Okay, let's say we take the traditional model or C model, where we consider variables to be just something that is, I guess, on a stack. If we do it that way, then it also means that eventually we will need to have some optimization paths, because constantly keeping everything in memory and on stack and doing it how we are doing right now, where we are just constantly when we're doing any operation, we load it, do operation on the register, then put it back on the stack, then load it again, and so on and so forth. So if that's the case, we will likely need some kind of intermediate representation to handle these kind of optimizations. So but before that, let's just think how we can in general deal with this stuff, right? So right now, if we look at the way operands are, so let me open, I guess it's value.h. Yeah. So these are all the different types of operands. But if we look over here, then we have stack and memory, and we do have to put immediate here. So this is something I definitely miss. So there are immediates. And immediates are, as I said, also interesting for this case where we want to say that we have a struct and immediately assign it some memory, or even array when we have like multiple elements. And we need to figure out what is semantics and how we're gonna treat that stuff. But what if we just said that these are the things that we have, right? We just have things on stack, we have things in memory, and we have things that are immediate, and we completely ignore the registers. So the registers would be something that is only there to perform operations and maybe later for optimization step. But we do not have that semantic in the language itself. It does not have that concept. And let's do two versions of that. One, as I mentioned, is with stack and memory, which is more like, let's say it's C-like. And another one would be, I don't know, it's called Java/C#/JavaScript, whatever, where we do not have stack. How would that, how the semantics look like for us? Okay, so if we do have a stack, then when we do something like int x equals 5, we know exactly what it's gonna look like. We will say reserve stack like we do right now. We say that the storage type, we're not gonna call it operand type anymore because it's not going to directly correspond to what is happening in the CPU, but rather this is like, where is the value stored? We say storage type would be a stack, and we reserve stack like we do right now. We do, and then we assign this immediate value to that location in the stack. And something else we'll figure out what does it actually map to. So we will, in both cases, as that we will need some kind of IR or intermediate representation. And this is more or less usually a higher level assembly language. Instead of mapping directly to instructions and knowing exactly how many registers are and all of these jazz, we can just do, we can do high level things. So in here we would say something like this may look like we have an instruction that is reserve stack, or even no, even the stack is probably gonna be implicit in this case. We just say it's more or less going to look exactly the same. So we would be in 4 byte x, and then assign x5, and I'm using the x86 assembly thing where target is on the left and source is on the right. This is what it might look like. Actually, in reality, it will not even look like that, but we need to introduce something in between. So let me quickly maybe do say, so there will be like 4 byte x as the thing, and then there will be 4 byte immediate 5 whatever $temp1, and here we say $temp1. So in these more high level things, we would ideally only manipulate uniform things, and that uniform thing will be some reference to a value, and the fact that it's immediate or it's on the stack will be handled separately from the fact that it's a value that can be performed operation on, right? And then once we have this, we could run optimization passes on it, and we could do all kinds of interesting things, and we can get into single static assignment forms, but I'm not sure I will. But this is more or less standard way to do it, and this is what we can do as well, and probably what we will do. And then after we have this, so if we are continuing towards this, once we have this simplified representation, then we have another box here that would take these simplified instructions, and actually it will be more like 2 boxes. So we'll have like 2 boxes. One of them is x86, another box is ARM, and it will generate necessary instructions, keeping the semantics that we specified. And as I said, there could be optimization here in between. There could be another optimization step afterwards. So there is a bunch of stuff that can happen. Okay, so this is kind of what we can go to. Something, and this is more or less standard. The other version where we ignore stack completely is something I didn't really think about that much yet, but I'm interested to explore, and this is sort of what this video is all about, me just trying to make sense of what we have right now and explore different possibilities, because I don't know the answer. I know the standard answer is that how like majority of language deals with that, but it's interesting to explore different things. Okay, so let's say if we go here, let's say we do not have stack. So we just have a concept of memory, and from the semantic standpoint, again, as I said, we can no longer write this. So this is not a thing that can happen in this universe. What happens is when you say int x, you actually say int star x, and then star x is 5. Right? This is what you're doing when you're doing this stuff in these kinds of languages. And if you don't have stack, our intermediate representation will still look probably very similar, and you could see how stack becomes an optimization, right? Because we would have some, actually here it should be x equals malloc whatever 4. 4 is because this is the size of int. And because this is the case, right? If we just directly translate it to some kind of presentation, we say x is, I will not say malloc, let's just say alloc of 4. And then I will use star x is 5, right? Let's just say that we have something like this, or it's assign 5, doesn't matter. Let's use assign, maybe. So assign x 5. I'm putting this in braces because we treat all of them as pointers. So x actually contains a location in memory where we want to go. And if we do it this way, then as its stack sort of becomes optimization, because if we go through this code, right, we have some function code, and let's just say we have return x as an extra instruction. And return is probably going to be in that intermediate representation as well. This is our function. We just say that we allocate 4 bytes, we assign it 5, and we return whatever we assigned. Now, if you look at this, it should be pretty obvious that this is completely unoptimal from the standpoint of what we actually want to produce, right? Because what we want to have is return 5. This is what is supposed to happen. But there are various ways how to take something like this and turn it into something like this. One of the ones I would like to explore, at least in the videos, which is called partial evaluation, and all compilers do it to a certain degree. Basically, we could start executing this program, right? We have this bytecode or high-level assembly, and we just run through it, and we, as an artifact of our run, we write out the remainder of what we couldn't resolve. So we would try to execute this statement and say, okay, we need 4 bytes. Okay, we will just magically create them somewhere. Then we say, oh, okay, actually we will write 5 to those 4 bytes, and then it should be like this. And then we return whatever is at that memory location. And we're like, okay, but we know exactly what is at that memory location. It's 5, so it's okay to be returned. Now here comes the kicker. This is also how C does optimization. So if I write something like this, we will get this, and this is something we can easily test by going to Compiler Explorer. So if we just say int test, I say int x is 5, then return x. Let me switch back to x86 so it's maybe slightly easier to read. Now, this stuff is more or less what we had in our IR that I just wrote. So we have some stack stuff. We move 5 to that location, then we move out 5 to the return value. And obviously this is very inefficient, right? So if I add optimization, it collapses back to what you would expect of like you can't return a value. You always need to like return this through the register. So it is the minimum that is there, but you can see it's exactly what we discussed should be the thing. Again, the interesting part about all of this is C is making certain assumptions about the semantics of your program, and in particular about aliasing of memory. So it's when you write something like this in C land, you're basically promising the compiler that nobody is going to touch the value of X in between this statement and this statement. I mean, you can also have something in between. You can say int y is whatever, right? But still, if you don't explicitly take address of X and pass it to somebody else, the compiler is assuming that nobody is touching that memory. And there is a whole bunch of things about aliasing and strict aliasing and why it's good, why it's bad. And there is a big discussion stuff you can find online if you want to. But the point of all of it is that for a language, you always have to decide, can the compiler make this assumption? If you do not make this assumption, you usually run into a wall in terms of optimizations, because you can't at any point in time assume that anything is static. So all of your semantics become slightly wonky. Now, you can force the compiler to not consider X immutable, right? So I think volatile is used wrongly in a lot of places. For some reason, it's got this into a point where people use it for concurrent code. And I mean, there are uses, but regardless, the actual use of volatile and the actual semantics of it is saying to the compiler that between this statement and this statement, somebody else might have come in and tampered with the value of X. And what it forces the compiler, it forces it to store it to memory, and every time X is updated, it will restore that to memory. So if I do ++X, what you will see happen here is exactly that, right? It stores X at location on the stack, then it loads it from the stack, it increments it, puts it back in the stack, and loads it again before returning. So this is what happens when you put volatile, and this is why you really don't want to put volatile in your applications unless you really have to, because essentially it disables almost all of the optimizations that the compiler does. Now, why I'm saying that? I'm saying that this is a decision that has to be made for the language. Another way you could get around this is you could separate your functions into pure functions and non-pure functions. And for example, saying that there are functions that are, and definition of pure functions is actually different between different languages, but the idea is that they don't produce side effects and they are kind of unobservable behavior. So you always give a thing to a function and you always get the same result back. And if you say that the function is pure, then the compiler can make all of these assumptions without necessarily having weird consequences on what is considered aliased versus not aliased value. Anyhow, for the purposes of this stuff, I think we will go with C model and saying, yes, you can consider values to be non-volatile as long as they are not passed to a different function. And if they are passed to a different function, maybe it would be cool if we would know that the function that we are passing it to does not actually store that pointer anywhere, and so that it's only volatile for the essentially for the duration of the call to the other function. I'm not exactly certain. It might be that this is sort of the semantics of C++ references. I need to look into that a bit more. Rust has that very explicitly, I believe, with borrowing, where you say, okay, I'll lend you this value for the duration of the call, but then you're sort of give me it back, and you can't use it afterwards. So there are various semantics that we could adopt, and those semantics, unfortunately, do influence the outcome of how you want to structure the stuff. But in the most simple case, we could do partial execution where we say, okay, we allocate this, we assign it to 5, and then we return whatever is there. And since we didn't find any references to this x outside of the things, we could just say that we need to return 5 as an optimization. Now, let's say that we did find a reference to, or we had this, let's say we introduced this concept of borrowing, and we have a call here, and we say we call some address, we call foo, and we pass x to it. We remove this. We pass x to the call to foo. Okay, if that's the case, then again, we need to figure out what does it actually mean. But if we go with Rust's borrowing, saying that only for the duration of the call, the value of x may change. So essentially, we can say we passing like const x maybe in C semantics, like const pointer. I'm not sure what exactly it's gonna call, but the idea is, yeah, we say that foo cannot really change x, it cannot save the pointer to x. Then once this is done, we now can no longer calculate this return value, right? We don't know that it's 5 because actually this needs to be other way around. So we first assign 5 and then we call foo. If that's the case, we no longer know that the return value is 5, but what we do know is that we don't necessarily have to create x in main memory. We can, like, our alloc essentially can decide, okay, I will actually give you something on the stack instead of something in main memory, like a dynamic allocation, but it's still considered a memory pointer and it behaves the same way. So after I talked about all of this stuff, we need to decide what are the next steps. And I think what I will do over the next few videos, I will try to prototype what this will look like, because it seems quite neat to me. It has less concepts than other stuff. And as far as instructions themselves go, so we will need to design our intermediate representation more thoroughly. But instead of design in abstract, again, because I can't hold all of that in my head, as we will do prototyping, like the prototyping will look like this. I will just take the current code, I will create a branch in Git, or I will just work on the current one, doesn't really matter. And I will try to figure out how can we get from where we are right now to a system like this. And I will look at the final code once it works and see, is it better, right? Because one of the things that you need to be ready to do if you're building complex systems is you need to be ready to fail. Like, there are only two ways how you can build such complex systems. You either spend a lot of time designing, like you need to exactly understand your problem scope and you spend tremendous amount of resources on like verifying and designing ahead and like making sure that everything works, or you try to build a small system, try to understand if that's a good way to move forward, and go for it. This happens not just in development, it happens in all industries, for example, I know space. But I think that this whole planning ahead is only really works when you have a ridiculous costs or danger associated with not doing that. So I don't know, if you're building a bridge, it would be pretty bad if you're just trying to build something and it collapses, right? But if there are no consequences, then I definitely prefer to just saying, okay, now I understand a bit better the system that I'm trying to build. Like, we have all of this code over here, right? We have all of these examples, we have the test, we have whatever. We understand a bit more of the system that this language should become. So now it's a good time to stop and reevaluate if the way things are going is the right way. And maybe after I do all of this, I'm like, no, that's actually not that great. And that's fine. Then we come back with this previous one, or we try this version, or we try some different version. It doesn't really matter what is the outcome of it is. The point is, we will try out different things, and maybe we will end up with some hybrid of all of this, but we definitely will get better understanding of the problem and the system at hand, and hopefully we'll get to a better application. That's probably it for today. If you stuck out that far, then thank you very much for watching, and I'm looking forward to trying this out in future episodes. Goodbye.